Okay, guys, so this week we're going to be talking about electric current and specifically about electric circuits. And so we're going to just kind of talk about the basics of electric circuits. And then next week we'll talk about different kinds of circuits and how these circuits are used in everyday life. So let's go ahead and draw a very basic circuit diagram, and then we'll talk about what each of these symbols means. Okay. All right, so for a basic circuit, we need three things. We need a battery that's going to be supplying our potential difference V that we'll talk about in a second. We need a resistor that's going to take the energy from these electrons that are moving and then convert it into some usable form, and we call that a resistor R. And then you need a conducting path that's going to direct our electrons throughout the circuit. And these moving electrons that are moving in the circuit we're going to denote as I, the current. Right? And current is the number of charges that's passing any given point per second. Right? So we just count up all of the electrons that are passing this given point every second, and that will give us our current. All right, so let's talk about the voltage. What purpose does the voltage serve in our circuit? So in this diagram, any battery is going to have a positive and a negative terminal. And this supplies what we call a potential difference. Right? So any electron that's in this wire is going to get pushed away from this negative terminal, and it's going to be pulled towards the positive terminal. So this particular electron in this wire is going to be pushed in this direction. Okay? And so the potential difference, the voltage, is a potential difference that supplies the force that pushes the electrons. You can think of this in the same way of a ball on a hill. So why does the ball roll down the hill? Right? It seems like a pretty self-explanatory question until you really think about, okay, why does the ball move? And it moves because the potential at the top of the hill, the gravitational potential, is higher than the potential at the bottom of the hill. So we have a gravitational potential difference, which then pushes this ball down the hill. And so we have the force of gravity that is a result of this gravitational potential difference. You can think of the voltage as being this hill that moves this ball or these electrons throughout the circuit. Right? They're analogous, but instead of gravitational potential, we're now talking about electric potential difference. All right, one thing that you might find interesting is the fact that, so the electrons are pushed from away from the negative terminal and towards the positive terminal. So electrons are moving in this direction. So why do I have my current drawn from going positive to negative? Right? And this is just turns out to be a happenstance of history. When electrical circuits were first being explored, right, it was talked about and debated whether or not it were the positive charges that were moving or the negative charges that were moving in the circuit. We now know that protons, positive charges, are held tightly in a nucleus and they do not move, right? Whereas electrons, which are on the outside of atoms, are the charge carriers, primary charge carriers, which move, all right? So they guessed wrong, and we never went back and corrected the direction of current. So current, we say, goes from positive to negative because that's how it was first defined, even though the electrons are actually moving in the opposite direction. All right, so a little confusing, but a pretty interesting history lesson nonetheless. Okay, so that's the potential, right? And we talked about current. Now let's talk about resistance. So the resistance will take the energy from these electrons and oppose their motion. So it takes the energy from the electrons and converts it into something else. The higher the resistance, the more it opposes the electron's motion, right? So, typically, for most resistors, it'll take that energy from the electrons and convert it into heat. So these resistors will actually start to heat up. This is how a light bulb works, right? As the electrons enter the light bulb, there's going to be a filament, and that filament will heat up due to this resistance. Right? It's taking the energy from the electrons and converting it to heat, and filament, whenever it heats up, actually illuminates. It gets light. So it takes the heat energy and then converts it into light, right? And so this is how electric circuits and light bulbs and resistors are important, okay? So we need to take this electrical energy from the electrons and do something with it, and that's what resistors are. All right, and we have an equation that relates all of these things in the circuit that we call Ohm's law. and the Ohm's law is voltage is going to be equal to the current times the resistance. And that's the equation that we're really exploring today, is what we call Ohm's law. So we're going to be changing our voltage and seeing how does that change our current, all right? And we're also going to say, okay, does the resistance change if we change voltage or current? And it turns out resistance is going to be constant for the most part. It changes a little bit based off of the amount of current, but really the resistance depends on mainly the material that our resistor is made out of. It doesn't change with the voltage and the current. All right, so we can change voltage by changing our battery. We can change the resistor by changing the resistor that we're using. And really the dependent variable here that we're going to talk about is the current. So it's really the current that's changing when we change these other two things. Whereas these are mainly determined by the battery that we're using for the voltage and the resistor that we're using for the resistance. Okay, so in the next part, we'll talk about some different types of materials and what materials are good at conducting electricity. And then we'll go about exploring how do we go about calculating the resistance of a material called nichrome wire. So we have a nichrome wire, and we're going to run some voltage through it, measure the current, and then from this equation of Ohm's law, we'll be able to calculate what the resistance of that nichrome wire is. All right, so we will be right back. Okay guys, let's go ahead and go through the exploration and experiment part of your electric current lab. So the very first part deals with just hooking up a few different batteries to a light bulb and making some observations based off of the brightness of the light bulb. So let's go ahead and do that. So we have our light bulb here hooked up. Either end of the light bulb is hooked up to either end of these two wires. And the first battery it wants you to test is the 9-volt battery. So let's go ahead and hook up to this 9-volt battery and see what we see here. All right, so we see nothing. Oh, it's because our bulb wasn't turned all the way. There we go. All right, so there we have our battery hooked up to our light bulb, and you can see the brightness of the light bulb. So let's compare that brightness now to the brightness of just a AA battery. So here we have our AA battery. Let's go ahead and just touch either end of our wires to the end of this battery. There we go. All right, so pretty dim, right? You can see it lighting up, but it's very dim, much dimmer especially compared to the 9-volt. Now let's do the D-cell battery. And the D-cell comes with this handy holder, so we don't have to worry about touching it to either end. Okay, and then you can see it's actually the same brightness that the AA was, and that might be surprising to you, but if you look at the voltage that is supplied by each of these, they both supply 1.5 volts. The difference between the two is that a D-cell battery will hold its charge for much longer, so it lasts a lot longer. So you typically use D-cells in jobs that will drain the battery quicker, whereas AA's are still supply the same amount of voltage, but they'll run out of their charge much quicker. So you want to use them for low charge devices that don't use very much voltage, or they don't draw too much current, so it won't discharge this battery quite as fast. Okay, now it wants us to add two D-cell batteries together, and you can see on the end of these they have two electrical or metal caps, so if we put these together, it'll actually connect these batteries in series. And so let's see what happens to the brightness of our bulb now. All right, so that's with one bulb, and if we can come back over here to a single bulb, you can see that it's about twice as dim. All right, so that's one bulb, and if we move this over so it's across both, you can see it gets a little bit brighter. Okay, so it's adding the two voltages of our batteries together to produce an even brighter. So this is kind of a midway between just the AA and the 9-volt. All right, so that's the first part of the exploration. The second part of the exploration is we're going to build a circuit to test whether or not certain objects will conduct electricity. So to do that, we're going to hook up our battery to one end of our light bulb, and we'll hook up the other end of the light bulb to one end of our battery. All right, and now if an object is going to conduct electricity, if we touch these two wires together here, you'll see that it lights up the light bulb. All right, so if we put something in between these two leads, if it conducts electricity, the light bulb will light up. So we have a few objects here. Let's just go ahead and test them really quickly. If we touch to glass, you can see it does not conduct electricity. If we use this penny here, you can see that it does conduct electricity. If we use our pencil and touch it to the wood, it does not conduct electricity, but if we touch it to the graphite, let's see if we can get this to work. Oh, there it goes. All right, well, if we don't get it to work this time, you'll just take my word for it. There it goes, it's lighting up there. So the graphite does conduct electricity. So pencil lead does conduct electricity. And the final one, we have our giant slinky here. So if we hook up it to one end and we just touch it anywhere on the slinky, you can see that it does conduct electricity. So metal conducts electricity, is the best conductor for electricity, and things like glass or wood are insulators and do not conduct electricity. Okay, so let's go ahead and move on to the next part, which involves using a crank generator. And we're just going to make some observations. So we want to hook up a generator that we're going to manually operate to our light bulb. And if we turn the handle of this generator, you can see it turns the light bulb. All right, so we want to do our best 1 turn per second. So 1, 2, and you can see that is the brightness of the bulb. So how does that brightness compare to what we saw with the batteries? And now if we go twice as fast, you can see there's the brightness. So which of our batteries did that compare to? And then finally, if we go 3 times as fast, how did that brightness? Which battery did that brightness compare? So you can make you can compare that brightness to the brightness that we saw with our batteries, and then compare the voltages, and so you can make an estimate about how much you think the voltage would be for those. And so the brighter the bulb, the more current there is, and the more current, the more voltage we're going to have through the battery. Okay, so that is it for the exploration. The next part is going to involve measuring the resistance of a nichrome wire. So there are 2 pictures in your lab, and we're going to set up the picture. So we want to hook up, we have an ammeter here and a voltmeter. This is going to measure current, and this one here, there's a glare, but it's going to measure the voltage across the nichrome wire. Okay? So we're just going to hook up this exactly like the picture shows. So the ammeter needs to be in series with our nichrome wire. So we just make a continuous loop from our ammeter to the nichrome wire. So there's our continuous loop. Right, if we go through here, you'd have to turn the other way. You can see that we're getting some current. Okay. Now with these ammeters, depending on where you turn, where you put the plug is going to depend on whether you read from the top or the bottom line here. So you can see that there's a bottom line and a top line, and depending on where you plug in your wire is going to depend on which scale that you read from. So if we plug this into the 1, we're going to read from the top scale, which goes from 0 to 1. So that's what we're going to do here. So you can see if I turn my generator, so I'm making current go through the wire, this is going to measure that amount of current. All right, now we need to hook up our voltmeter, and voltmeter needs to go in parallel to our function generator. So we just need to hook up one end of our function generator, or not a function generator. We need to hook up one end of our manual generator to one end of the voltmeter, and then the other end of the voltmeter is going to hook up to the other end of our generator. So if I turn this now, you can see that it's reading the voltage and the current at the same time going through this nichrome wire. So it's going to give you 3 voltages that it wants you to turn your voltmeter, or that it wants you to supply. So depending on how fast you turn the generator, right, is going to depend on how much voltage you're supplying to your nichrome wire. So the very first one it wants is 7 volts. So we need to turn this generator until this gets up to 7. And once we get this to 7, we're going to read our current from our ammeter. So let's go ahead and do that. Let's see if I can position these so that you can kind of see them. Okay. All right, so we got it up to 7 volts. And then from that, we can then, as that's at 7 volts, you would have been able to read the current from the ammeter. Okay, you can see though, it is difficult to keep it constant. So a lot of your error is going to come from being able to keep the voltage constant while you're spinning this generator. So you have to just do your best to try to keep it as constant as you can, and then to read the current. All right, and that's the gist of this lab. Is just it gives you different voltages at different currents, and then from those you can then measure the resistance of our nichrome wire by just using Ohm's law. Okay, and then you would do the same way, but instead of the full length, we would measure the half length of the wire. So we would come down here. So now we're measuring only the resistance of this, doing the same procedure. There's one more demonstration that I want to show you before we call it a quits on this video here. Instead of our ammeter, let's go ahead and use our light bulb, which is going to be our current indicator. It's going to let us visually see how much current is running through our circuit. And instead of our generator, let's hook up just a battery that's going to supply a constant voltage. We don't need our voltmeter anymore for this. This is just a demonstration. There we go. All right, so we just have our battery, our nichrome wire, and our light bulb all hooked up in series. And so if we touch, if it wants to stay on, there. If we touch this to our nichrome wire, it should light up. Now, since it's applying a constant voltage, depending on the resistance of the nichrome wire is going to change how much current is running through our circuit. So if we come down and we decrease the length of our nichrome wire, you can see that our light bulb gets brighter. And as we come to the other end, all the way down here, it gets dimmer. So as we increase the voltage of our nichrome, or increase the length of the nichrome wire, we're increasing the resistance, which is decreasing the current. So one more time, as we decrease this length, we're decreasing the resistance, which is why the bulb is getting brighter. Oh, my arm is in the way. Sorry, guys. Let's try that again. So as I decrease the length, the bulb gets brighter. And as I increase the length, the bulb gets dimmer. And it's because the longer the wire, the more resistance it has. Okay, that's going to do it for this demonstration for this part of the lab. With all of that, you should be able to answer all the questions. All of the values are been recorded for you, so you can do the needed analysis to calculate resistance and whatnot. All right, so that'll be it for this time, and we will see you next time.